right. So today we're going to talk about a couple different ways to fit curves to data. First, we'll use some matrix methods to do linear regression, and then we'll do some nonlinear regression. So when I talk about matrix methods, what do I mean? Well, say we have some data. Just got some data, and let's say it's fairly straightforward. You know, kind of looks like it's following some sort of linear trend, but it's a little messy. It's not perfect. And we look at this data, and we instinctively go, okay, there's sort of this upwards trending diagonal line, and we could sort of imagine drawing a line of best fit through it. But we want to make a choice for the slope of this line and the intercept of this line that are the best fit. And we don't just want to be choosing randomly and hoping, because this case is fairly straightforward to kind of see what the line of best fit is, or at least what would be close to it. But if the data is either of a more complex form or the data is messier, it might not be so straightforward. So for that reason, we want a rigorous way of determining what line fits our data the best. So let's think about how we tackle this information. What we'd be given is a list of two lists of numbers. We'd be given a list of x values and a list of y values, and they'd be in pairs. So we'll have some x value for this dot and some y value, and on and on and on. So we can write that down in an abstract list. So we've got x1, which is maybe this x value, and x2, which is this x value, and so forth on in increasing increments, all the way to our final x, however many data points we have, and we'll just call that xn. And for each x, there is in this data set, for each x there is a y. So we will have a y1 and a y2, and so forth, and on and on and on, all the way to yn. It's not by chance that I'm leaving a big blank space here. We'll get to that. Now, in this simple case that we're looking at, we may be familiar with the equation for a straight line, which is y is equal to mx plus b. And that, if this is a straight line, which it was my attempt to draw a straight line through this data, it would follow some equation like this. And so the process of choosing the line that fits this data the best is the process of choosing the m and b that will create the line that fits this data the best. So we could theoretically, if all of these x's and y's were perfectly on a line, we could just, for each pair, we could write that y is equal to m times an x plus a b, and just have done. The problem is that no m and no b is perfectly going to satisfy all of these data pairs. They're a little messy. There's some deviation from a perfect linear trend here, and so it's a little bit of a head scratcher. How do we choose an m and a b that is the best compromise between all these data points that are pulling in slightly different directions? And so this is where the matrix methods come in. We're going to write all of these. Instead of writing y is equal to mx plus b many times, we're going to write those equations in matrix notation. And what do I mean when I say matrix notation? Well, I mean we're going to have a little vector, which for our purposes right now is just a list of numbers. A vector that has an m and a b in it. And we've got our column of x's here, and I'm also going to put a column of 1's here. And if you're not familiar with this kind of thinking, you'll see what I mean in just a moment. Though this is matrix and vector multiplication, how it's written, matrix and vector notation, and the way these two objects, this matrix and this vector, it's a matrix because it's got multiple rows and multiple columns. We're going to take this vector and we're going to kind of bring it up here and we're going to tip it on its side, and this m is going to multiply each x, and this b is going to multiply each 1, and so and then we'll add in a row, and that should get us over here to this y. So we'd multiply this m times this x, add 1 times this b, and that should get us a y1. Now, of course, because so we do that for each row, all the way from the beginning to the end. Let me put our y vector in brackets as well, just so we keep things tidy looking and uniform. As I said before, this line is not touching all data points. So when we actually do this, well, m times x plus 1 times b, we might not get y equal to 1. We'll get something that's very close to it if we've got a line that's a good fit for the data. But m times x1 times 1 plus 1 times b might not exactly equal y1, and that's our problem here. How do we find an m and a b if m and b don't multiply with this row to make y? Well, again, here's where some of the matrix methods come in. So if you have ever had anything to do with linear algebra, you may remember the idea of a matrix inverse. A matrix, here, let me skip over here for just a second. A matrix can be thought of as a transformation of space. And so say, let's come back here. Say I had the matrix 4/3 and 2/3 and 2/3 and 4/3. Just a little 2x2 matrix. The way you can think of this matrix is it's going to take every point on a 2D plane to some other point. And so if I had, say, the vector 1, 1, and I go through this matrix multiplication process, well, I'll go 1 times 4/3 plus 1 times 2/3, which is 6/3 or 2. And I'll do the same thing down here, and I'll get a 2 again because it's the same numbers. So I have this matrix of values, and when I multiply 1 with the point 1, 1, it takes me to the point 2, 2. And that can be visualized like this. So if I have my point 1, 1 here, and I move my, there we go, and I move my my initial vector in the x direction, sort of the 1, 0 vector, I move that to the point 4/3, 4/3, 2/3, and I move the original y vector 0, 0, 1 to the point 2/3, 4/3. That's another way of saying what's happening here. We're taking the vector 1, 0 and moving it to this new position, and we're taking the vector 0, 1 and moving it to this position. And so these are sort of two different ways of saying the same thing. We're just visualizing the movement of this point to this point via this transformation. So the matrix inverse is sort of an opposite transformation that cancels out the effect of the first transformation and takes us back to our original state. And the way this looks in math is the matrix inverse. When you multiply a matrix by its inverse, you get something called an identity matrix. And so if we can somehow, the thing about an identity matrix is that any vector multiplied by the identity matrix is just itself. And so it's sort of the matrix version of multiplying something by 1. If you multiply any number by 1, you get that number back, and the 1 doesn't affect it. So if I can somehow turn this matrix here into the identity matrix by some series of operations, that will isolate this M and this B, and if I've isolated it, that's just like regular algebra. I've solved for what these values are. So that's what we're going to do. So we need to somehow perhaps using this matrix inverse thing we were just talking about, we need to eliminate this matrix here. One thing, this matrix, however, is not square, and a square matrix, it's much easier to have a matrix inverse of a square matrix. So what we're going to do is we're going to make this matrix square, and then we're going to find the inverse of that matrix. Let's give things some proper names. So I'm going to call this matrix actually has a special name. It's the design matrix, and more on that in a little bit. But so I'm just using the letter capital X to symbolize this whole matrix, and I'll use the letter C to symbolize this vector, and I'll use the letter capital Y to symbolize this vector. So how do we get this thing to be square so that we can get a matrix inverse? We're going to multiply this matrix by its transpose. And all a transpose is we take this matrix and we rotate it so that this corner comes up here and this corner goes down here, but these corners stay in place. And so that would look like x1, x2, ... xn, and our ones come along for the ride. That's a funny looking one there. Let's be a little bit more precise. There we go. ... So there's our transpose of x, and the way that we would write that down in notation is we'd say x with a little t up in the corner. That's the symbol for x transpose times x times c is equal to, and we're going to, just like regular old algebra, if you do something to one side, you have to do it to the other. So we're going to multiply y by x transpose, and it's important we multiply it from the left side, because when you're multiplying matrices and vectors, it's important which side you multiply from. They're not equivalent. So, and I'll just indicate with an arrow over here that we're multiplying this vector also by x transpose. So when we do this matrix multiplication, even though we've got many more numbers in a column and in a row than we did over here, it's the same process. We're going to take this entire column, bring it up, and kind of tip it on its side, and x1 and x1 will multiply each other, x2 and x2 will multiply each other, on and on, element by element, and then we'll sum the whole thing, and then we'll have this column interact with this row of ones in just the same way. x1 will multiply this one, x2 will multiply this one, and so forth, and then we'll do the same thing with this column and this row and this column and this row, and at the end of this whole process we'll have a new matrix that is a 4x4 matrix. Now it's not important, it's not necessary that you produce a 2 by 2 matrix. It's not vital that you produce specifically a 2 by 2 matrix, but it is important that you make the matrix square. We might have more complicated data, and we'll look at some more complicated data in just a moment. Well, a little later on. So now we've got these two things together make some kind of square matrix. I'll put a little parentheses. And so now this matrix, we need to multiply it by its inverse. And so we'll do that. And the way we would write that notationally, we'd say x t x to the -1. That's how you signify an inverse matrix. Times xt times x. X transpose times x times c is equal to, and just as before, whatever we do to one side, we have to do to the other side. So let's go x transpose x. I'm in the danger zone where my head is overlapping with the text. Let me move this over. Okay, to the -1 times x transpose times y. And all of this is equal to, I'll come up here so I'm not writing behind my own head. All of this is equal, so all of this here, this x transpose x quantity to the, well, not quantity, but to the inverse times xt times x, all of that is equal to a 2 by 2 identity matrix, which just looks like 1 0 0 1, and so any vector that's length 2 that we multiply by this, we'll just get c back. So we've got I2 to signify it's a 2 by 2 identity matrix, I2 times c, which is just equal to c. So if we're able to find this expression here, then we will get c as our final product. So that's in principle how this stuff works. Now, it doesn't have to be for a straight line. We can apply these methods to much more complicated and maybe intimidating looking expressions, as long as they satisfy certain as long as they have certain properties. Let me clear this away. And so we're going to take these methods and look at what might seem a little intimidating. We're going to look at the Antoine equation. The Antoine equation is a way of relating the vapor pressure of a liquid with the temperature. And it looks decidedly like something that you couldn't handle with a method like this. But we'll just do a little bit of oh, that should be a minus b over t plus c. So I know we were just working with x. Let's write that a little more cleanly. T plus, looks like a j. T plus c. So I know we were just working in x and y. Now our independent variable is t, temperature, and our dependent variable is well, you could think of it as being the p vap, the vapor pressure, or you could think of it as being this whole thing here. And our constants, before we had a vector of constant c which had m and b in it, and now our vector of constants is going to have a and b and c in it. We hope. That's what we're shooting for anyway. So we'll have some data in a moment. We'll take this into Python, but we'll have some temperature data, and we'll have either some vapor pressure data or just directly log 10 of the vapor pressure data, and we're looking for A, B, and C that satisfy this data in the best way. Just like we were looking for an M and a B that satisfied our data the best in the last example. And so let's massage this equation a little bit so that we can use some of these matrix methods. What we're looking to do is, let's just do it. So let's take our log 10 of the vapor pressure. I'm just going to call it PV. And let's just multiply both sides by T plus C so we can get it out of the denominator here. So T plus C. And since we're multiplying both sides by it, let's do that. So we've got A times T plus C. And we've got a minus B. All right, and so let's distribute things out. Log 10 of the vapor pressure, PV. Let's put the T in front so it doesn't look like we've got our temperature inside the log 10 expression, plus log 10 PV times C. Put the C in front, and all of that is equal to A T plus A C minus B. Now we're actually, let me rewrite that. That is not particularly legible. But we are actually now very, very close to a form where we can use the methods we just I'm going to drop the 10 just because we're a little low on space. But I'll put the 10 there. All right. So all we need to do now is move this over to the left side, and we will have something we can work with. Now you might be saying to me, Garrick, how in the world this isn't a relationship between we don't have log 10 of the vapor pressure over here. How is this helping us? Well, we know that this relationship exists, but right now the thing that we're trying to do is find C and A and B. And so if we can get this equation into any form where we sort of have we have a function of one variable plus another function of that variable, or a function of that different variable, and we're not in the situation where we've got a function that's composed of multiple functions. Here we've got sort of two functions here. We've got this t is to the negative 1 power, but it's also t plus a constant. So we're not in that situation anymore, and so we can adapt I don't remember if I called it the design matrix before, but we can adapt the design matrix approach that we took before to work for us here. So in this case, our design matrix is going to, instead of being just a column of x's and a column of 1s, we'll have a column of log p's and a column of t's, and this will treat this whole thing as a new constant, which we can call once we go through this process and we get a C and an A and a D, well, D has A and C in it, so we can use our values of A and C to solve for B. And so our design matrix will have a column of log vapor pressures, and a column of temperatures, and a constants column with just ones in it. And so this will be log PV1 and temperature 1, and just as before, we're going to have a whole bunch of rows, log PV2 and temperature 2, and on and on and on to the nth row, which is down here, and all that will equal T1 times, this row will equal T1 times log 10 PV1, which I'm not going to write out, but we'd have our corresponding temperature times log vapor pressure, and all this times our vector C will equal this a vector of temperature, vapor pressure, log product. Okay, so let's take this into Python and try and make some magic happen. Oh, you can see I was working on this before. All right, so let's get rid of some of this stuff, and let's make a new Google Colab document. New notebook. And if you haven't worked with Python before and you're wanting to give it a try, this is a really excellent way to get started, because you don't have to download anything, and so you can just start experimenting straight away. It's called Google Collaboratory. We'll call this Antoine, because it's the Antoine equation. All right. So let's put our programming hats on. The first thing, let's get some actual data to work with. So we're going to use the wget command, and there's some data that I'm going to be working with that is right here in GitHub, and I'm going to get the raw and use this link. And that's our data that we're going to be working with. So let's run this. All right, we've got the data, and it's here in our files. In content. That's the default location. So the water vapor pressure CSV. I'm just going to copy the path now. Before we go too much further, let's bring in our primary workhorses that we're going to be using today, and those are first NumPy. So we're going to import NumPy, which stands for Numerical Python. If you haven't used it before, it's a very popular library of mathematical functions and tools. So we'll import NumPy as NP. We'll from plotly.subplots we'll import make subplots, and then this is just a cosmetic thing, but if you prefer the dark theme, you can do this. This will make the charts default to a dark theme. We'll import plotly.io as pio, and we'll set pio.templates default equal to plotly dark. Let's run this just to make sure that everything is kosher, and all you need to do to run in this environment is press Shift Enter. All right, it would have told us if something was wrong, at least something something was wrong in the syntax, and we'll probably see that at some point during this video. So we've got NumPy. Let's read our data in, because we've got the file, but we haven't read it yet. So we'll go np, which remember is NumPy load text, and we will specify the file path, and we will say that our delimiter, the thing separating the columns of data, delimiter, there we go, is the comma. And if you saw that the file extension is CSV, that just means comma separated variable. So it's your hint that your delimiter, your thing separating the columns of data, is going to be a comma. So let's give this thing a name. We'll just call it data. So that's the name of the information that we're going to be reading in. Let's run that, and let's take a look at it. All right. So here is our data that we're going to be working with. This is the data that we're going to be trying to draw a line of best fit through. And the first column is in temperatures, to all somewhere in the low to mid hundreds, and this column is not log, not any log of the vapor pressure, but the vapor pressure itself. And the hint there is just the order of magnitude it gets up to, in the millions, or tens of millions, right? Yeah. That would be a very, very large log if that were I don't know what the pressure itself would be if this was the log. Okay, so we've got our data. Let's get these columns into variable names that describe them. So let's just call this first column, we'll call it temperature, or we'll call it T actually, and T is data. We'll do a little slicing here. Data. We want all rows of the first column. So we'll do the colon for all rows, and the first column is specified by 0 because Python indexes from 0, like many languages. And let's also get this column. We'll just call this column PV for vapor pressure, and PV will be data. And we again want all rows, but we don't want all rows of the second column, which is specified by index 1. And since we're thinking about the log 10 of the vapor pressure, let's get that as well. So we'll call it log PV. We'll remember that it's log 10. That's just to have a nice short name to be working with. And our log PV is going to be np log 10 of our PV vector. All right, let's run all this. Okay, nothing seems to have gone wrong, but let's take a look anyway and just make sure that our data looks like we're expecting it to. So going to make a quick little matrix called all using this numpy C underscore method, which just takes different arrays and concatenates them as columns in a new matrix. So T and PV and log PV, and we'll print it and have a look at it. Print all. Okay. So yeah, all right. So yep, the calculations look right. We've got the order of magnitude here matching the exponent, the power of 10, which is just what it should be. Okay, so we've got our data. We've got it in some variable names. Now our next thing is we want to have our design matrix, so that we can start to do some of these matrix thingies. So let's make our design matrix, and we'll just call it capital X like we did before, and we'll use this npc underscore tool again, and let's see the order. Let's have it be log PV. That'll be our first column, and T will be our second column. Right? Is that right? Yes, we've got log of our vapor pressure, temperature, and then a constants. Yep, that's what we've got. So for our column of ones, we're going to use np ones like, and all ones like does is give us a vector of ones, or a matrix of ones that's the same shape as some other vector or matrix. So we're going to do ones like t, and that'll just give us a vector of ones that's the same length as t. And so let's do that. Let's stop printing all. Don't need that anymore. Okay. So now we've got our x, and oh, the other thing we need, because remember, our data here is t times log PV. So we're going to need a column that is that. So let's get that as well. So we'll say that. We'll just give it a descriptive name. We'll call it t log PV. And we'll just do a straightforward element-wise multiplication. And that we can just write as t times log PV. And you know what, let's put that in our matrix that we were using to look at things before. Again, just to make sure that everything looks like it should. T log PV. And we'll print all. Okay. So this column's T, this column's P, this column's log PV. Does this column look like it's this number times this number? About 300, about 3, about 900. Yeah, okay, so it checks out. You can check the last, I suppose. We've got about 21 million, about 600. Oh, no, we've got about 7 and about 600. And yeah, it checks out to be, that's pretty close to, yeah. Okay, so all is good with the world. So now let's if we remember the expression that we were using before to turn all of this into the identity matrix, and the expression that we want is here, where y is our t log PV now. So let's recreate this expression. And so we'll say let's do this in a new. Run this again to get rid of all that printout. So let's call our vector C. That's what we're gonna be keeping our constants in. And let's say, well, remember, so we started with our y, our sort of our answer data, which in this case was t log PV. So t log PV, and that's just a name. That's not the math. The math is happening right here. So we multiplied it from the left by x transpose. That got erased. Multiply it from the left by x transpose. So the way you specify that it's a matrix multiplication rather than just a regular multiplication is using the at symbol. That's what you use in Python for matrix multiplication. So multiplying it from the left by x transpose, the way you specify a transpose is just with a dot t. And then we want to multiply this whole thing from the left by that inverse expression. And so we're going to use np linalg, short for linear algebra, dot inverse. Let's get a space there. And it was the inverse of x transpose multiplied by x. So there we go. Yes, x transpose times x, all of the inverse of that whole expression, and then that whole thing matrix multiplying this from the left. So let's give this a go. And it didn't throw a fit. Let's print C and print C to see what we're working with. Okay. So if we recall, our first constant is -c, our second constant is a, and our third constant is ac minus b. So let's say c is equal to negative, and we'll index inside this c vector we created negative the first position, so that'll give us a -34, and we'll say that a is equal to just the second index in this vector, and then we'll say b is equal to c is equal to a, well, is equal, so if we wanted, if we had AC and we subtracted this thing, the ACs would cancel and we'd have minus b, so which would be positive b. So let's just do that. We'll say a times c minus lowercase c index 2. And that should get us our a, our b, and our c. So let's run that. Now, something I didn't do at the beginning is I didn't plot our data to take a look at it. So before we try and see what line is generated by these constants, let's plot our data. So to do that, we'll create a figure, and we'll just name it fig. Fig is equal to make subplots, and we're just going to have one subplot. We could specify multiple rows or multiple columns if we wanted multiple subplots in a single figure, but we're just going to do 1 and 1 for now. And let's do something to our figure. Let's add a scatter plot, and our x values are going to be our temperature, and so x is equal to t, and our y values are going to be, and we have a choice here. We could do we could just do the log PV, or we could graph the pressure itself directly, and it's fine either way. I'm going to graph the log y is equal to our log column, which is, remember, we just called log PV. And it's important that it'll default to graphing a line without the data points, and we want to see the data points. So we'll set the mode equal to markers. And there's a lot of other cosmetic things we can do, but this is the bare minimum. And so let's take a look at our data. Okay, and that's a pretty wide plot. So we'll fig update layout, not layout, layout. Fig update layout, and we'll set the width and the height. We'll say width equal to 600, and height is equal to 400. 400. There we go. All right, and we'll. Okay, so there we go. There's our data. We could have done that in the beginning, but we've got it now. So now let's make another plot. Let's make let's make a line on this plot and see how well our constants fit our data. So we'll do another add scatter. Fig add scatter. And we'll set our x data. We'll set our x data equal to our temperature, and we'll set our y for our y data. We'll just directly enter the formula using the constants that we've found, we've extracted. So y is equal to a minus b divided by t plus c, and it's that simple. We can just enter it. And let's set the mode to lines, because this time we do want a line. We're not graphing specific data points. We're trying to see if our line fits well. So ain't she a beaut? She's going right through all the points. Now you may notice there are some regions here where it seems like the line is suddenly going straight. This would probably be more obvious if we'd plotted the pressure itself rather than the log of the pressure. But you can kind of see it down here. It's curving, and then it goes straight from this point to that point, and that's because it really all it's doing is connecting the points. And so everywhere that we have a temperature point, it's calculating the height that the y that it should have, but where it doesn't, it just directly connects the points. So if we want, we could, instead of making x our temperature data, we could make x we could create some temperature data that would just fill the same range. So we'd go linspace from the minimum temperature to the maximum temperature, and I don't know how many data points do we can do 50, sure. And let's see, is that syntax? It might throw a fit if I'm doing something wrong. Linspace. Yeah, okay. Let's give it a shot. Whoa, that's interesting. I think somehow this is yeah. Min-t, max-t. That is funky. I think this is what comes of trying to do this. I'm sure I probably made a mistake trying to do this formula inside. So let's do it outside and then plunk it in. So we'll call it graph t is equal to np.linspace from min t to max t, and yeah, 50 data points sounds fine. And we'll just, yeah, okay. It didn't throw a fit, so the syntax should be right. And then we'll just say that x is equal to graph t. And fingers crossed. Oh, I didn't update the temperature in here. That was the problem. Graph t. There we go. All right, that should take care of that. There we go. And now we've got a nice curve, and you can see it's a little bit more rounded there and rounded here. All right, so this is how you handle equations that you can break down in a linear way. What do you do if you get an equation that this method can't solve? Well, that's a very good question, and I will show you. This was a linear regression. Let's do some nonlinear regression now. So let's see. Yeah, I think the only thing we need to import that we don't already have is from the SciPy library, which also has a lot of useful stuff in it. From SciPy, optimize, import, minimize. And I'll explain what all this is for in just a moment. So let's how to explain this. So if you can't use these matrix methods, what you can do is create the equation in the computer in code, and just give some initial guesses for what A, B, and C are, because that's what we're looking for right here. We're looking for values for A, B, and C. So if we feed guesses that we know are probably wrong, maybe very wrong, into the equation, we can get some answer. So if we look at our equation here, if we were to just plug some random A, B, and C into this equation, it would give us some value, and we have the real value, so we can compare the value that our guess for A, B, and C are, and see how far away it is from the actual value. And we can do that for every temperature, and then we can. Some of our guesses might be too high, some of our guesses might be too low. So what we can do is we can square them all to make them all positive, since the squaring will get rid of any negative signs if I'm getting ahead of myself. Well, we can quantify the difference between our actual data and our guess data by subtracting one from the other. And if our guess was too high, then we'll get a positive number, and if our guess was too low, we'll get a negative number. And so if we square all of those just to get rid of the negative signs and positive signs, we can get our code to try and get guesses that make how wrong we are progressively smaller. And that's what this minimize thing is going to do. So first, let's define a function. I'm just going to call it Antoine. And this Antoine function is going to take in a guess for A, B, and C, and it's also going to take in a vector of temperatures. So A, B, C. These are different from the capital A, B, and C I was using above. These are just variables to be used by this newly defined function Antoine. And we'll just say all this is going to do is calculate A minus B divided by T plus C, and we'll just return that value. So I'll just write return. I'm not going to give it a name. Highlighted when I shouldn't. Oughta. Return A minus B divided by T plus C. So there's our equation. Now this business of taking our guess and subtracting the real value from our guess, and using that as squaring it and then adding up all the squares, that's called the sum of the squared errors, and so we're going to use that as our measure of sort of globally how wrong our guesses are. And so let's make a function for that too. We're going to define Antoine, we'll call it Antoine SSE, and we're going to let's make a vector of guesses. We'll say our guess for A is equal to some value, and our guess for B is equal to some value, and our guess for C is equal to some value. And I mean, we can cheat if we want, you know, and look at the values that we know are right, but let's say we didn't know. We just had a sort of an order of magnitude idea that this, you know, we thought, okay, well, our A is probably going to be somewhere in the low double digits or high single digits, and this is going to be also in the double digits, and remember it will be negative, and then B will be somewhere in the thousands. So I don't know. Let's say A. We'll just say A is. We'll say A is 9, and we'll say B is 1,000, and we'll say C is negative 20. Maybe that's doing too much work for it. I'll say -1. And after we've gone through this once, we can start. We'll start with a. For fun, we can start with some further out values and see at what point it won't converge to the right values. So now let's make a vector, which I'll just call x0, and oh, I think I need to make these floats and not, because I think if I just keep them without the decimal point, they'll be read as integers, and that might make some issues for us. So we'll just make this a little array with our A guess, our B guess, and our C guess. All right. Bam. All right. So we've got all our constants, and so that's going to be our first input into this sum squared error function is a vector of constants. And then we also need the parameters to calculate the vapor pressure from the Antoine equation, and that's just the temperature. And then we need our actual data to compare our guess data to. So that was, if I recall, what did I call it? Log PV. Yeah. Log PV. All right. So first, we calculate. We use the Antoine equation to calculate our guess. So we'll say we'll just call it guess. Guess is equal to Antoine, and we will have our inputs for A, B, and C, which are just x0, 0, and x0 index 1, and x0 index 2, x0 index 2, and our temperature vector, of course. And is everything looking good there? Yeah. First constant, second constant, third constant, and no brackets in wrong places. All right, and then we'll get our actual sum squared error. So we'll call this SSE. And so remember, we started by subtracting the actual data from our guess from our guess data. So we'll guess minus log PV, and then we will hold take that whole thing and we'll square it. And this double multiplication, this double star is how you specify to the power of in Python. And then we'll sum our squares, and we'll just do that using numpy sum. Okay, all right, and then we'll return this sum squared error. Okay, so we've got our two functions. Just to make sure that I don't have anything wrong syntactically, I'm going to run this. Ah, there's always something. Ah, every time. Gotta have a colon at the end of your function defining line. Okay, let's try now. Okay, no obvious syntax problems. So now we'll use the minimize that we imported. We'll say, I'll call it minimized. Minimize is equal to minimize. Let's just have a name for the process that we're going through. Minimize, and so the first thing, yeah, we will have fun, but the first thing we're going to enter is our function. And so the function that we're minimizing is the sum square error. So Antoine SSE. And the next thing is, oh, it's even called XO in here. The next thing that it wants is the vector of constants that we're going to be varying. And we called it x0. And then it also needs any other arguments that go into that equation. And so that's the temperature and the log of the vapor pressure. So we'll say args equal to T and log PV. And it's important that they be in the right order, because it's this T and log PV here. I maybe should have used a different variable name just to make clear that it's not this function is not built to take in only those vectors. It can take anything that it takes in that's in the second position of when you call the function, it will treat as the temperature. It will do whatever it does to, it will feed that into the Antoine equation, and it will subtract whatever you put in the feed in as the third position. It will subtract that from your guess. So that's why it's important to enter these in the right order. All right, and the last thing we need is a tolerance. Let's see. Yeah, we need a tolerance, and so tolerance we'll set equal to 1e to the negative 10. And I think that's that. So let's try it. Oh, ogpv. You don't know what ogpv is? Well, you can't be blamed for that. Okay, so it ran with no apparent issues. Let's take a look at our constants that we've arrived at. So this n here is number of iterations, and it's 32. That's reasonable. Okay, so and down here at the bottom we've got our three values. So let's compare them. We've got about a 10.2. Let's print out A, B, and C just so we can compare them. Print. We can print them down here. Well, no, let's print them up here. Print A, B, C. Oh, we want capital A, not lowercase a. Print A, B, and C. So 10.2. About a 1770. Okay, fairly close, and negative 34, negative 36. Okay, so we're very much in the same ballpark. A little bit of variation, but not a tremendous amount. And so just like before, we can take this data and we can graph it. And so if I were to load these values into an A and a B and a C. I need to call them something slightly different, so I'll call them A1 and B1 and C1 is equal to minimized dot x. And so that this whole body of data is minimized, and it has this x. So that's all I'm specifying here. I've got this vector of 3 values, and I'm loading them into A1, B1, and C1. And so let's do that. And then let's also add this to our figure, and we can compare the fits and see how different they are visually. So we'll go fig add scatter, fig add scatter, and our x values will be let's use the graph temperature that we used before, graph t, and our y values will just again be the equation using these constants. So y values will be a1 minus b1 divided by graph t plus c1. Let's take a look at this. Oh, and we want to set the mode to lines. Mode to lines. Let's take a look. What did I do wrong? Positional. Oh, yes. I need to say that this is my y data. Y is equal to. All right. There we go. And it appears that our two traces are right on top of each other. We can try and zoom in, see how far. Yeah, so we really zoom in, we can see a difference, but it's fairly small. So I hereby pronounce this mission accomplished. We've looked at 2 different ways to fit the same data, and I hope you've learned something, and that you've had an informative. How long has it been? I had an informative time. Thanks for watching. Bye.